Welcome. In this lecture, we'll begin to explore functions that have a scalar argument. An important part of this is we'll need to be able to understand the derivatives. And so that's what we'll look at right now. What we're going to do in these multiple sessions for this lecture is we're going to explore the idea of a derivative of a function that has a vector argument. We haven't looked at that in prerequisite courses, so what we'll do is we'll jump back into some prerequisite material where we have a function that has multiple variables. That's very close, but not exactly the same. So the main concepts that we want to look at are this idea of a partial derivative of something that has a vector argument. We'll look at the directional derivative in particular, and there's an idea closely allied to that that's called a gradient. We'll develop a Jacobian matrix for a function that has a vector argument and has a vector result. And we'll end these sessions talking about the level curve of a function. The sample problem that we could have is, suppose we have a weather map and we want to know how much does the temperature increase if we're at some location in that weather map. Let's recall the idea of a derivative. So let's take an example from basic physics. Let's suppose we have a long, thin rod, and it doesn't matter what material this is made of, but suppose that this rod is heated so that it's a uniform temperature, and then we drop it into a bath of cool flowing liquid. What will happen is that rod will begin to cool. And we're scientists, so we're going to measure this in degrees Kelvin. What we would have is, on the horizontal axis, we would have, for example, time, and on the vertical axis, we would have, for example, degrees Kelvin. And what we would see is that that rod would start at some temperature, and then it would exponentially decay to some other temperature. And we could write that as a function of a single variable, and we could then compute the rate of change of that function with respect to its scalar argument. And let's observe the units of this. So the units of this are, the function has units of degrees Kelvin, and the argument has units of time, for example. And so the units of this would be degrees Kelvin per unit time. And if we said, after a certain amount of time, what is the temperature, we could answer that. When we start to get into these derivatives, it gets a little complicated. So if you can't remember how to work with a function and an argument that have different units, this would be a good time to go back to some of that prerequisite material. Next, let's take that long, thin rod, and let's consider a slightly more elaborate example. Suppose that long, thin rod is at some uniform temperature. It could be room temperature. And suppose that simultaneously we apply heat to one end. So what we're thinking of is we have a rod here, and at one end of the rod we increase the temperature substantially, and then at the other end we decrease the temperature substantially. So we're heating one end and we're cooling another end. And now the question is, what is happening to that rod? Well, to be a little more specific, a little more scientific, what we can say is, suppose that we could measure instantaneously, continuously, any place along this rod at any time of interest, starting with time 0. Well, then we would have two variables, right? So here we have two variables, and let's call them t for time, and so time, and we have distance. And if we have time and distance, then what we have is the temperature of any spot on that road on that rod is given by when we measure it and where we measure it. So what does that do? Well, that now is a much more complicated thing to look at, because this function will depend on what we're doing. If we wait just a little bit of time, then this will have increased in temperature and this will have decreased in temperature. So the temperature that we read depends on how long we've waited, and it depends on where on the rod we're measuring the temperature. So this turns out to be a problem in thermodynamics, and it can be solved under the appropriate assumptions using some techniques from applied mechanics and physics. For us, what we need to appreciate here is that there's a very simple physical system that we can imagine quite easily that can be written down, and it has two variables, and these variables are all different, right? So this has the units of time, this has the units of distance, and this, being a temperature, has units of degrees Kelvin. So we have three things going on, and again, if you're a little bit unsure of what, for example, the partial derivative of this with respect to time, what are the units? So you can ask yourself, what are the units? And you can look that up, and then you can look up what it means for what the units are for the rate of change of this with respect to distance. And then a question is, how can you combine these in some nice way? And that is what we're going to start to look at. What we'll do is, instead of dealing with these as independent variables, towards the end of this lecture, we want to deal with them as though they're entries of a vector. Now, let's recall some of the basic calculus from prerequisite courses. The idea in a scalar function is this maps a real number to a real number, and we'll often write this in functional notation. The first derivative of this is defined as a limit. That is, we take the derivative at time t, or at scalar argument t, is defined as a limit, which is if we add a tiny amount to t, evaluate that level, take t, evaluate that level, that the difference in these levels divided by this variable, at the limit of that is defined as the derivative at that argument. So what are some natural extensions? Well, the first extension that we'll explore is what happens when the function has a vector argument. The next is what happens when we have a scalar argument and a vector function. And then the most elaborate case is what happens when we have a vector argument and a vector function. So in multivariable calculus, also prerequisite material, the way that we'll write it is, instead of using x's and t's or something else, what we'll do is we'll refer to this as W1 and W2. So for now, we have a function that has two arguments and produces a real number, and we'll refer to these arguments as W1, W2. So the partial derivatives are, again, from prerequisite material, a very straightforward extension of the partial derivative for a scalar argument. Here, what we do is to find the derivative with respect to argument 1, what we do is we hold argument 2 constant, and then we take this small amount, add it to argument 1, do the evaluations in the division, and the limit of that is the partial derivative of the function with respect to the first argument. The partial derivative of the function with respect to the second argument is likewise defined.